In previous section, we learned how to store unstructured data in cloud storage. But we also need to store transactional data as well. And when we talk about transaction, first thing that comes in our mind is SQL database. Generally, such transactional data has fixed schema, and we need to store such kind of data in some form of RDBMS solution. So, how to store such data in Google Cloud? To answer this question, in this section, we will continue our learning journey about storage option in GCP with another storage offering in Google Cloud, that is Cloud SQL. Cloud SQL allow you to store data in RDBMS solution like MySQL. Since RDBMS is very common technology nowadays, so I will not spend time on explaining about what is RDBMS. Rather, in this section, I will explain how you can leverage the RDBMS technology in Google Cloud. What are the Google Cloud offerings to support this? Google Cloud offers two services to support RDBMS requirement in cloud, and these services are Cloud SQL and Cloud Spanner. Cloud SQL compete with RDS service on AWS, and currently Cloud SQL has fewer options as compared to RDS. Currently, Cloud SQL allow you to run either MySQL or Postgres or SQL Server instance in cloud, while AWS RDS service has many options. Since Cloud SQL is like a traditional RDBMS solution, so for scaling, it follows the scale-up approach and not the scale-out. From a customer experience and convenience perspective, Cloud SQL is a fully managed, no-ops database service. This makes it very easy for you to implement SQL database in cloud, as Google will set up, maintain, manage, and administer your relational database on Google Cloud Platform. On the other hand, Cloud Spanner is a Google proprietary homegrown service, and unlike Cloud SQL, it offers horizontal scaling as well as multi-region replication. Cloud Spanner can scale horizontally to handle any dataset size, and to meet the scaling requirement, it requires you to increase the number of nodes and consequently the cost. You can also install your own SQL database such as MySQL on a VM using Compute Engine. And in this case, you will have to build the schema, manage and administer the database yourself. This method gives you all the freedom and flexibility to run your database in the same way as you were doing in your on-premise database. But there are certain benefits that you can use when you use Cloud SQL as a managed service, instead of running your own database instance on a Compute Engine VM instance. So in next video, we will talk about Cloud SQL features, which makes it a better option as compared to running your own database instance on Compute Engine VM instance. In this video, I will discuss features of Cloud SQL, which makes it a better option to run SQL database in Google Cloud, rather than running your database instance on Compute Engine VM instance. So, Cloud SQL is a fully managed relational database service for MySQL, Postgres, and SQL Server. Cloud SQL can scale to a high-capacity database which is capable of handling the terabytes of storage. Accessing and using the database in Cloud SQL will be exactly same as like any other RDBMS, which means you can simply run your SQL type queries such as select statement to read the data from table or insert statement to write the data in database. By using Cloud SQL, Google ensures the performance and availability of the database service and takes care of the database management, patch management, and replication. Google Cloud offers a powerful database in the form of Cloud SQL, which provides your application the reliable and secure storage, along with the sufficient space and speed of operation. Google Cloud SQL is ideal for the small to mid-sized application. Cloud SQL does not require any maintenance or software installation, and it is not difficult to use at all. Since it is implemented on cloud, so you do not need to set up any VM physically. This makes it far more attractive than running your RDBMS on a VM instance. In this case, Google manages common database management tasks such as backup and archival. Cloud SQL also provides tools to migrate your existing RDBMS data to cloud, and you can easily do the scaling and customization of Cloud SQL instances. Cloud SQL also supports other applications and tools that you might be familiar with, such as SQL Workbench, Toad, and other external applications that use the standard SQL driver. Cloud SQL, like any other RDBMS, provides the strong asset support, and you can easily integrate Cloud SQL with existing applications and cloud services like App Engine, GKE, etc. With Cloud SQL, you can easily configure replication and backup of your data in cloud. In case of Cloud SQL, it is also possible to enable the automatic failover to make your data highly available. Cloud SQL support the data encryption for both data at rest and data in transit. Though you can run MySQL instance in Cloud SQL, still there are few differences between standard MySQL instance and MySQL instance running in Cloud SQL. For example, user-defined functions are not supported in Cloud SQL, but some services which you need to enable and configure in standard MySQL are automatically provided by Cloud SQL as part of the managed service. Like MySQL replication feature requires good amount of configuration and design thought in your on-premise standard MySQL deployment, but it can be enabled as part of Cloud SQL managed service by just few clicks. This replication feature will replicate the data between multiple zones and provide the automatic failover without loss of service. Cloud SQL also provides automated and on-demand backup with point-in-time recovery option. And like your on-premise MySQL instance, you can easily import and export the database using either MySQL dump or via import and export CSV file utility. One of the primary features of Cloud SQL that is difficult to reproduce in your on-premise database is its scalability. Though you need to restart your SQL instance to scale up, but it is still much easier as compared to your on-premise database. You can also scale out easily by using the read replicas in case of Cloud SQL. Whenever you need to choose between a standard MySQL instance and Cloud SQL managed service, then you should try to answer few basic questions like, do you have any specific OS requirement or custom database configuration requirement, or you need some special backup requirement. If that is the case, then perhaps you want to consider hosting your own database on a VM using the compute engine. Otherwise, it is strongly recommended to use Cloud SQL as a fully managed service for your relational database requirement. Now, let me show you how to create your first MySQL instance in Cloud SQL. To create a MySQL instance in Cloud SQL, click over here and then select the SQL option under Databases. Here, if your project does not have any Cloud SQL instances, then you will see this dialog box suggesting to create an instance. Now click on Create Instance. Here you need to choose which RDBMS you want to create in Cloud SQL, and you can select any of these three RDBMS options from here. For this demo, let's select the MySQL option. Here you need to define the instance ID, root password, location, and the database version for your MySQL instance. So let me give a meaningful instance ID name over here. Also set the password for your MySQL instance. Here you can choose the region and the zone where you want to create your MySQL database. Then here you can choose the database version which you want to create. Here, if you expand this show configuration options, you will notice that here you can provide additional information for your MySQL instance like labels, flags, or connectivity. Under connectivity, you need to choose whether you want to use the private IP or public IP to connect with your database server. Under backup and recovery option, you can define the schedule for the automated backup. Here you can choose any time window based on your convenience. Here you can also enable or disable the point-in-time recovery option for your MySQL instance. This point-in-time recovery option helps you to recover an instance to a specific point in time. For example, let's consider a case where some error causes some loss of data in your database. In that case, you can recover your database to its state before that error occurred. A point-in-time recovery option always creates a new instance, and you cannot perform a point-in-time recovery to an existing instance. In this case, the new instance inherits the setting of the source instance. And this point-in-time recovery is enabled by default whenever you create a new Cloud SQL instance. Here, you can decide whether you want to create your instance in a single zone or you want to create an instance in a multiple zone in a single region. Definitely, multi-zone instance provides higher availability as compared to single zone. Here, you can choose the machine type to be used for your database server. Here, you have many choice what kind of a machine you want to use for your database server. Either you can use the shared core machine or you can use standard machine or also you can use the high memory machine. Machine type that you select here will determine the number of cores and the memory for your Cloud SQL instance. Here for this demo, I will select this shared core machine and click on select button. Also notice that the performance of the network depends upon the number of CPU in your machine. If you choose a machine with more number of CPU, then the network performance will also go up. This behavior is very much similar to what we have already seen in case of Compute Engine VM instance as well. Here you can select the type of storage and the size of storage as well. You can either select the SSD storage disk or the HDD storage disk for your MySQL instance. Just remember that SSD disk gives the better performance as compared to HDD disk. Here you can give the size of the storage disk for your MySQL instance. If you want that your storage capacity should increase automatically whenever it is about to finish, then you should enable this checkbox. Here, based on the storage selection, you can see the disk throughput metrics and the IOPS for your disk. Overall performance of your instance will depend upon the number of CPU and the memory parameters that you select in this section. Here, you can also decide how your data should be encrypted in your MySQL instance. Do you want to use the Google managed keys or you want to use the customer managed keys for the encryption of your data in your instance? Here, you can set the database flags for your MySQL server. You can use database flags for many operations like including the adjusting the MySQL parameters, adjusting options, and configuring and tuning an instance. For this demo, I will not add any flag. Under this maintenance section, you can configure your maintenance schedule, like on what day of the week you want Google to run the maintenance for your server instance and in what order related to the other instance. Here, you can select any day of the week as per your convenience. Here, you can assign labels to your VM instances. We have already seen why to use labels in other services as well, like Compute Engine and GKE. Labels helps you to organize your instances. For example, you can organize your instances by labeling them by your cost center or environment. Labels are also included in your bill, so you can see the distribution of your cost across your labels. Just notice that Cloud SQL is not a serverless offering by Google because here you can control the configurations for your VM for your Cloud SQL instances. Now click on Create button to create your MySQL instance. It will take some time for your instance creation. I will pause this video until this SQL instance is created. Now this SQL instance is created. Here you can see the connection details for your SQL instance. You can connect to this instance either via command line or from your application or from any UI based SQL client as well. Here you can see the configurations like number of CPU and the memory allocated for your SQL instance. Here you can see the maintenance configuration for your SQL server. If you want to check logs for your SQL Server instance, then you should click over here and it will take you to cloud logging where you can analyze your logs. If you want to see the operation logs performed on your SQL Server instance, then you can check it from here. Cloud SQL allows you to connect to SQL instance VM, and if you want to connect to that VM, you can connect to it by clicking over here. But in this case, your client VM from where you are trying to connect to Cloud SQL instance VM must have static IP address. In previous demo, you have learned how to create a SQL instance in Cloud SQL. Now we will create a sample database and some sample tables inside that database. But before creating a database, let's first connect to the SQL instance via Cloud Shell. To connect to this SQL instance via Cloud Shell, you need to click over here. This Cloud Shell instance uses the gcloud SQL connect command to connect to the SQL instance. You can also type this command in any other Cloud Shell instance as well. Now click enter over here. Once you press enter, it will take some time to allow the IP address of the VM that is running your Cloud Shell session to connect with this Cloud SQL instance. After this, it will ask for the password. Just enter the SQL instance password over here and press enter. So here you are connected with the SQL instance, and this is the very familiar MySQL command prompt, and you can type any command over here. Let's try to get the list of existing database first. So here you can see the list of default databases which are created for you in this SQL instance. Now let's check the current database. So I have not selected any current database. Now use create database command to create a new database. So here you have created a new database. So your database is listed in this list now. Now I will create a table inside this database. Okay, so I have not selected any database so far, so I am getting this error. So let me use my database first. Now I will create table inside this database. So I have created the table inside this database. Let me check my table in this database. So your table is listed in this database. This is how you can connect to the SQL instance via Cloud Shell and create a database and the table inside your SQL instance. If you want to see the list of database or want to create a new database via UI, then you can click on this link. Here you can see the list of databases in your SQL instance, and you can also create a new database by clicking on this button. In Cloud SQL, you can also import database from the external database in your Cloud SQL instance. You can do this database import using both UI and via command line. Like if you want to do it via UI, you just click on this import button over here. Here you can import your database either using the SQL dump or the CSV data. You just keep your source database dump or CSV file in one of the cloud storage bucket which you can access and give path to that bucket over here. You can also specify the destination database name if database name is not specified in the source backup file, and then you can click on the import button. After this, your database will be imported in this SQL instance, and time taken for this data import will depend upon the size of the source database backup. In previous chapter, you have learned about Cloud SQL, which is a data storage service in Google Cloud to store the relational data. In this chapter, we will look at another relational data storage service in Google Cloud, that is Cloud Spanner. Cloud Spanner is a fully managed relational database service with unlimited scale and strong consistency, and it provides up to 99.999% availability. At first glance, both Cloud SQL and Cloud Spanner might look similar to you, but Cloud Spanner is different from Cloud SQL in many aspects. Cloud Spanner is a Google proprietary technology, and it is not like open source databases like MySQL or Postgres database. Cloud Spanner is a fully managed, strongly consistent relational database service, which means you do not need to configure and manage SQL VM instances separately like Cloud SQL. Everything is fully managed by Google. It provides all features of SQL database like SQL queries and ACID compliance. Cloud SQL instances are vertically scalable and instances are confined in a region. But Cloud Spanner is a globally distributed and horizontally scalable database. It handles replicas, sharding, and transaction processing automatically so that you can quickly scale to meet any usage pattern and ensure success of your products. Cloud Spanner is designed specifically to combine the benefits of relational database structures with non-relational horizontal scale. Cloud Spanner offers transactional consistency at global scale. Just like Cloud SQL, it supports schemas and automatic synchronous replication for high availability and business continuity. Cloud Spanner is built on Google's dedicated network and it is tested by Google services used by billions. It offers high availability with zero downtime for the planned maintenance and schema changes. Cloud Spanner delivers industry-leading 99.999% availability for the multi-regional instances, and it provides transparent synchronous replication across region and multi-region configurations. Since it is a managed RDBMS service, you do not need to manage lot of database management activities in this case. With Cloud Spanner, creating or scaling a globally replicated database is much easier than Cloud SQL. You can even get flexible pricing for those times when you do not need to access the database. This is useful for enterprise applications that are only utilized during work hours. Cloud Spanner optimizes performance by automatically sharding the data based on the request load and the size of data. As a result, you can spend less time worrying about how to scale your database and instead you can focus on scaling your business. With Cloud Spanner, your application users can be anywhere across the globe. Application backed by Cloud Spanner can read and write up-to-date, strongly consistent data globally. Additionally, when running a multi-region instance, your database is able to survive a regional failure as well. Cloud Spanner users can make schema changes like adding a column or adding an index while serving traffic with zero downtime. To ensure data security in Cloud Spanner, data is encrypted inside Cloud Spanner and it is very well integrated with IAM for defining the access and the control with comprehensive audit logging. Cloud Spanner also supports on-demand backup and restore, and it has client libraries in many popular languages like C Sharp, C++, Go, Java, Node.js, PHP, Python, and Ruby. Since a long time, developers have built their applications using traditional databases like MySQL or Postgres databases, and they were able to run their applications successfully for a long time. But nowadays, most of them are facing challenges in terms of scaling their databases with the traditional database. So they have started to opt out for the various NoSQL databases. NoSQL databases solve the scalability concern, but most of them does not provide the transactional capabilities. This is where you will find Cloud Spanner is a better choice because it combines both the world of RDBMS for the transactional support and the NoSQL database for the horizontal scaling. Cloud Spanner provides both the capabilities. Also, Cloud Spanner provides high availability and automatic replication as compared to traditional database. When you talk about traditional RDBMS solution, then you either might be running something like single host MySQL database, or if you are an advanced user, you might be running MySQL database with failover and read replica capabilities. Any such configurations require some downtime if you need to apply some kind of a database patch or the software update. Though you can minimize this downtime by using the failover feature, but still some downtime will be there. But with Cloud Spanner, there will be no downtime required for all such things. It will remain available all the time, and all this is seamlessly managed by Google for you. Now we have understood that both Cloud SQL and Cloud Spanner provides relational database capabilities in Google Cloud. So how to decide when to use Cloud SQL or when to use Cloud Spanner? Generally, you prefer to use Cloud Spanner when you need to handle data size more than 10 terabytes and you expect your query per second to be more than 5000. Cloud SQL is a regional service, and on the other hand, Cloud Spanner is a globally available managed database service. So it is preferred to use when you have customer base present globally in all the regions. If you have already tried traditional SQL and hit by the vertical scaling limit of your master instances, then you should think about the Cloud Spanner because it provides horizontal scaling. It can easily scale to handle petabytes of data and very large number of read and write operations. You can also use Cloud Spanner where you need to consolidate data from the various data sources because of its capability to handle high read and write operations. Traditionally, you use ETL job to bring data together from the different data sources into some data analytics solution. Now you use Cloud to consolidate your data into Cloud Spanner and use its SQL-like query interface to interact with the consolidated data. Since Cloud Spanner is a highly available database and data is automatically replicated synchronously, so it is preferable database solution for a use case where you need to make large transactional intensive operations such as financial trading system, e-commerce transaction, and inventory management applications. In previous section, you have learned how to store relational data in Google Cloud using Cloud SQL or Cloud Spanner. But there are many use cases where you do not need the relational feature of the database, but you are more interested in highly scalable database. In such case, you prefer to store your data in another offering from Google Cloud, that is Cloud Datastore, or you can say Firestore. Cloud Firestore is the latest generation of Datastore in Google Cloud, and it is a document-based database like MongoDB. Datastore is not strongly ACID compliant, but it follows the eventual consistency. Datastore works best when data that you need to save is hierarchical and highly structured. If you have data which is non-hierarchical or unstructured, then Bigtable is probably a better choice of technology that you can use. Stores data in terms of key and values, and it supports indexes as well. If you are storing immutable blobs such as movies, which might be greater than 10 MB in size, then cloud storage would be a better choice. Now let's look at some of the features, workload, and use cases for Cloud Data Store. Cloud Data Store is a highly scalable and fully managed NoSQL document database from Google, and Data Store follows the eventual consistency. This allows you to concentrate on developing your application rather than concerning yourself with the capacity planning and trying to forecast for anticipated load. Cloud Data Store handles both replication and sharding of your data automatically, and it supports both regional and multi-regional replication. In case of regional replication, it provides 99.95% availability, while for multi-regional replication, it provides 99.9% availability. You store data in RDBMS in a table in terms of rows and columns. But in document database, entities are of different kind. In Cloud Data Store, entity is similar to a row and kind is similar to a table. Similarly, the way rows in RDBMS table contains columns, entities in data store consist of properties. Data store is different from RDBMS in terms of many operations, like it does not support join, filtering, or subqueries. Data store provides REST interface to interact with the database, and you can use this feature to integrate your applications using Cloud Data Store. Data Store is a schema-less database, so you do not need to worry about making changes to your underlying data structure as your application evolves. Datastore provides a powerful query engine that allows you to search for the data across multiple properties, and you can sort your data as well as you need. Cloud Data Store ensures the integrity of your data by executing multiple data store operations in a single transaction with asset characteristics. So all the grouped operations succeed or all fail. Cloud Data Store is not as strongly asset compliant as your RDBMS is, but it's a balance between the strong consistency and eventual consistency. So where can you use this NoSQL Cloud Data Store database? Traditionally, RDBMS use relational data, that is rows and columns. There is no hierarchical relationship within those entity relations in case of RDBMS. Data store, on the other hand, is document-oriented database, which makes it more optimized for hierarchical structured data such as XML or HTML. This NoSQL database will allow you to store structured data for your web and mobile applications. If these are your typical use cases, then you should consider using Cloud Data Store. Like, you can use Data Store to store information like gaming session state, user profile information, or product information in case of e-commerce application. Now let's do a quick check about the similarities and the difference between RDBMS and Cloud Data Store. Both RDBMS and Cloud Data Store support the atomic transaction. In RDBMS, data is stored in terms of tables, rows, and columns. On the other hand, data store use kind, entity, and properties to store your data. And RDBMS use primary key to uniquely identify a row, but data store use key for the unique identification. In RDBMS, some queries use indexes for the fast data retrieval, but in Cloud Data Store, all queries use indexes for the fast data retrieval. Whenever you store an entity in data store, index is also created implicitly for every property unless you specify not to create index for a particular property. You can also create composite index in Cloud Data Store. And in RDBMS, query execution time is dependent on the dataset size, which means amount of data in a table. But in data store, query execution time is independent of the dataset size. In RDBMS, all rows in a table follows the same schema, but in Cloud Data Store, entities in one kind does not need to follow the same schema, and these entities represent structured hierarchical data. From exam perspective, it is very important for you to understand these differences so that you can decide when to use RDBMS and when to use Cloud Data Store for a given scenario in your exam. In your exam, you will rarely get a question based on how to add an entity in Cloud Data Store or writing a query for the data store. This exam mainly focuses on reasoning behind choosing the right data store technology for the given scenario. Now I will show you how to use Firestore and store entities inside the Firestore in Google Cloud. To use Firestore in Google Cloud, you first need to choose the Firestore option under Database. Cloud Firestore is the latest generation of Cloud Data Store, and you can use Cloud Firestore in either native mode or the data store mode. Here you can see some of the comparison between both the modes. Like native mode does not support App Engine, but Datastore mode supports all the runtime environment. If you need to capture real-time or offline data from your mobile or the web application, then native mode provides the library to capture such data. But on the other hand, Datastore does not provide any library for such kind of use case. In native mode, data is stored in terms of collection, document, and fields. But in Datastore, data is stored in terms of kind, entities, and properties. Native mode can handle maximum 10,000 write per second, but in case of Cloud Datastore, there is no upper limit. It scales horizontally. It is recommended to use Firestore in Datastore mode for any new project because it comes with many new features and it can easily support millions of write per second. Whatever mode you select over here will become permanent for this project. And you must read and understand this note very carefully while deciding the database mode. Once you select any of these modes, you will not be able to roll back this for your project. For detailed comparison between two modes, you can go through the page link that I have attached in the resource section. For this demo, let's use the Datastore mode. On this page, after selecting the Datastore mode, you need to select the location where you want to store your data. So here you have two choices. Either you can create multi-regional Firestore or you can create the regional Firestore. In case of multi-region, it provides 99.999% availability, but in case of region, it provides 99.99% availability. So for this demo, I will go with the region option. So let me select one of the region from here. Now click on Create Database. Here you are getting this option to switch to native mode because you have not created any entity so far in your Firestore. Once you create your first entity, then this option will disappear. Now let's create an entity in your database. To create an entity, you can click either over here or you can click on this button as well. So let's click on Create Entity button. To create an entity, first you need to define the namespace for your entity. Namespace is like the partition for your entity. Most of the database requires only single namespace, but if you want, you can add multiple namespace as well for your database. For this demo, I will use the default namespace. Then here, you need to provide the kind for your entity. Kind is like a table in your RDBMS. Here, either you can type a name for the kind which is already created, or you can type a new name and your kind will also be created with your first entity. So here, let me create first kind. Here you need to provide the key identifier for your entity. It can either be numeric ID, which is auto-generated, or you can choose the custom name as well. So for this demo, I will use the auto-generated numeric ID. Here, if you want to specify the parent-child relationship between two entities, then you can define it over here. Now here, you need to add the properties for your entity. To add a property for your entity, click on Add Property button. Here you can provide the name, type and value for your property. So let me add a property over here. By default, index will be created for this property. If you do not want to create an index for this property, then you can deselect this option. After adding a property, click on Done button. To add another property, click on Add Property once again. Now click on Create button to create your first entity. So here your first entity is created and you can see the value for the properties that you have defined for your entity. And this ID is the auto-generated ID for your entity. So this is how you can create an entity in your data store. If you want to create more entity, then you can do it in a similar way by clicking on the create entity button once again. Also notice that that option to switch back to the native mode is gone now because you have already created one entity in your data store. You get that option to switch back to the native mode unless you do the first write in your data store. Once you do your first write in your data store, then you will not get that option to revert back to the native mode. Here you can see that you are using the Firestore in the data store mode and this is the location for your data store. On the dashboard page, you can see the stats for all the kinds in your data store. In the index page, you can see the composite indexes that you have defined for your application. Currently, you have not defined any composite indexes for your application, so nothing is appearing over here. This is all about data store in Google Cloud. If you have any queries related to this, please post your queries. In addition to Firestore, Google Cloud has another NoSQL database offering to store your data, and this offering is Bigtable. Bigtable is a fully managed columnar database service provided by Google, and Bigtable is very much similar to Apache HBase database. It is also used by Google in its own services like Search, Gmail, Maps, and Analytics, etc. You normally prefer to use Datastore when you need to store hierarchical structured data, and Datastore can handle data size up to few terabytes. But Bigtable can handle data that can be in petabytes as well. It is a very high performance proprietary data storage solution provided by Google, and it is based on technologies like Google File System and SS Table. In Bigtable, you can easily store billions of rows and thousands of columns. It can be easily used for applications that need very high scalability. You prefer to use Bigtable for large analytics related use case or in use case where you need to store time series data. Now let's talk about some of the features and the use case where Bigtable can be used. If we talk about the features and the use case for the Bigtable, then I would say that Bigtable is ideal for storing very large amount of data, and it supports very high read and write throughput at low latency for the fast access to large amount of data. You can scale the throughput of the Bigtable linearly, and you can increase the query per second by adding the more Bigtable nodes. Bigtable can scale seamlessly to handle from thousands to millions of read or write per second. Bigtable throughput can be dynamically adjusted by adding or removing cluster nodes without restarting, which means you can increase the size of a Bigtable cluster for a few hours to handle a large load, then reduce the cluster size once again, all without any downtime. In case of Bigtable, you can achieve high availability by creating replica cluster for a Bigtable instance. Once this replica is created, you just need to write data once into the Bigtable and your data will be automatically replicated to the replica cluster asynchronously. Bigtable follows the eventual consistency model. Since it is a fully managed service, you do not need to do anything manually to achieve this high availability by using multi-cluster replication. Bigtable provides 99.99% availability if you set up multi-cluster replication, but for a single instance cluster, it provides 99.9% availability. If you have an existing application that is using HBase, then you can easily migrate your application with very minimal changes. In addition to this, you can also connect Bigtable to Google Cloud services such as BigQuery, Dataproc, or other Apache ecosystem. You should use Bigtable if your data is structured and you want to perform some analytics with low latency. Since Bigtable also supports to store time series data, so you can also use it for building a recommendation engine where you can build your model using historical data which is stored as a time series data in Bigtable. You can easily store and consolidate market data, trade activity, and other data such as social and transactional data using Bigtable. Some of the real world use cases where Bigtable is getting heavily used these days are financial data analysis, IoT, AdTech recommendation, and market data analysis to identify the customer preferences and their purchasing pattern. You can also store graph data in Bigtable. In addition to these use cases, Bigtable can also be used as a storing engine for your MapReduce batch operation. After Bigtable, next NoSQL data storage offering in Google Cloud is BigQuery. BigQuery is a serverless, highly scalable, and cost-effective multi-cloud data warehousing solution designed by Google. You can say that it is one of the most compelling reasons to use Google Cloud. Google offers this data warehousing service at very cost-effective price, and it is very easy to use as well. Amazon also offers its data warehousing solution, that is Redshift. But in case of Redshift, you need to provision nodes first like Bigtable, and more node means better performance. But in case of BigQuery, it is completely serverless. You do not need to provision cluster or create indexes. Or I would say that you rarely need any ops work in case of BigQuery. This makes it really very easy to use, but it also means that you have less control on performance in this case. In case of BigQuery, you do not need to deploy any resources and keep track of them, or even worry about scaling them. All of this is handled by Google, and you can directly run your queries efficiently and save the ones that you need to retrieve later. BigQuery also supports many data input formats like CSV, JSON, Apache Avro, ORC, and Parquet. BigQuery allows you to scale to petabyte, and it is targeted at the enterprise data warehouse for analytics market space. You can easily analyze petabyte of data using SQL-like queries using BigQuery. BigQuery also provides ODBC and JDBC drivers at no cost to ensure that your current applications can interact with its powerful engine. You must always remember that BigQuery is designed as a data warehousing solution, so it is best suitable for analytical OLAP type of queries and scanning large amount of data. It is not designed for transactional type queries, or you can say OLTP queries. For OLTP workload, you better use Cloud SQL, Cloud Spanner, or Bigtable. You can easily ingest data into BigQuery from various sources. You can do both streaming data ingestion and batch data ingestion. Like you can ingest data in BigQuery at real time using Cloud PubSub and makes this data available for real-time analytics. You can do batch ingestion from Bigtable or Cloud Datastore as well. BigQuery transparently and automatically provides highly durable replicated storage in multiple locations, and it provides high availability with no extra charge and no additional setup. When you load data into BigQuery, each column of the data is stored separately. The value in each column are compressed and encrypted, and the corresponding data file is replicated. Each of these replica is then stored in the underlying distributed file system known as Colossus. There are four ways to interact with BigQuery in Google Cloud. You can interact with BigQuery using Cloud Console. This is a UI-based web console to interact with BigQuery. Next, very common way to interact with BigQuery is BQ command line utility tool. You can use this BQ command line tool in Cloud Shell. Other ways to interact with BigQuery are REST API provided by BigQuery or client libraries provided for various languages. Most common operations that you perform on BigQuery using any of these tools are loading or exporting data, query your data, and managing your data. You can load data into BigQuery using both batch operation and stream operation. With batch loading, you can load the source data into BigQuery table in a single batch operation. For example, Data source could be a CSV file, an external database, or a set of log files. Traditional ETL jobs falls into this category. You can also load data from cloud storage or local file system as well. And these records can be in Avro, CSV, JSON, ORC, or Parquet input data format. With streaming, you send the data one record at a time. You can either write code that calls the streaming API directly, or you can use Dataflow with Apache Beam SDK to set up a streaming pipeline. Once your data is loaded into BigQuery, you can run both interactive query or batch queries to analyze your data. You can also create view, which is like a virtual table, or you can also use partition table to query a subset of data. In addition to querying and viewing data, you can also perform data management operations on BigQuery like creating dataset, deleting dataset, create tables, listing of jobs, etc. We have already seen BigQuery in brief while discussing about billing export. But now I will talk about BigQuery in more detail. To use BigQuery, you need to select the BigQuery option under Big Data. Whenever you want to use BigQuery, first thing that you need to select is the dataset, which contains your data. Dataset in BigQuery is like a database in the relational database. A dataset is contained within a specific project. Datasets are the top-level containers that are used to organize and control access to your tables and views. A table or view must belong to a dataset, so you need to create at least one dataset before loading any data into BigQuery. BigQuery also has number of publicly available datasets that you can play around with, or you can build and train your data models using those datasets. The storage for such datasets is completely free. It means storage for the publicly available datasets is paid by Google, so you only have to pay for the queries that you run against these datasets. And these queries will be charged like any other query. You can see those publicly available datasets over here. In case these publicly available datasets are not visible to you, then you click over here and select the Explore Public Dataset option from here. Then from here, you can select any publicly available dataset. Now let me select the COVID-19 publicly available dataset from here. So for this demo, I will use this publicly available COVID-19 dataset. And this is the table inside this dataset. Here you can see the schema of this table. If you want to see the preview of some data inside this table, then click over here. Here you can see some of the data inside this table. Here on this tab, you can see the details about the table. Like here, you can see the fully qualified name of the table. This shows the size of the table. And here you can see the expiration of the table. If you want to write some queries, then you can write it over here. Or you can also select the previously executed query from the query history. So I will use this query from the previously executed query. Now you need to click on the Open Query in Editor. This query will show you the number of people who are found COVID-19 positive in US. Also notice that before executing this query, here you can see the estimate about the amount of data that this query will process. It is one of the best practice to use BigQuery that you should always check this information before actually executing your query. Now to run this query, click on Run button. And here you can see the result of this query. You can also see the response in JSON format by clicking over here. If you want to see the execution details about this query, then you can see those details over here. Like here you can see elapsed time, byte shuffled, etc. You can also save this query for the future use by clicking on the Save Query button. Similarly, you can also schedule this query to execute for some other time by clicking on Schedule Query button. If you want to format this query, then you need to select the Format option. Now you can see this query in a nice formatted way. In any practical use case, you would prefer to create your own dataset rather than using public dataset. If you want to create your own dataset in BigQuery, then you need to select the project first from here and then click on the Create Dataset button. Here you need to provide the unique ID for your dataset. Next, here you need to choose the location for your dataset. You should choose location nearest to your compute capacity or near to your customer. Whatever location you choose over here cannot be changed after this dataset is created. You can choose any location from this list. For this demo, I will use the default location. After this, you need to choose the default expiration period for the tables inside this dataset. You can either say that the tables will never expire in this dataset, or you can define the default expiration for the tables in terms of number of days. Any new table created in this dataset will be automatically deleted after the specified number of days after table creation. This is useful for the temporary data which does not need to be preserved. And these are just default values. You can also define table expiration at the table level. If you define value at the table level, then the table level values will override the default values that you defined over here. Next, you need to choose how you want to encrypt your data. You can either choose the Google managed keys or you can choose the customer managed keys to encrypt your data. For this demo, I will use most of the default option. Now, you need to click on the create dataset to create your first dataset. Now your first dataset is created. Here you can see the details about this dataset. Now to load data into your dataset, you must first create tables inside this dataset. In BigQuery, every table is defined by a schema that describes the column name, data type, and the other information. You can specify the schema of a table when it is created, or you can create a table without a schema and declare the schema in the query job or the load job that first populates the data in the table. To create your first table inside this dataset, you need to click on the Create Table button over here. Here in this source field, you need to choose how you want to load data into this table. You can either create a blank table or you can load data in this table from various options like cloud storage, local file system, Google Drive, or the cloud Bigtable. If you choose the local file system option here, then here you need to provide the location of the local file that contains the data. Let me select the local file for the sample data. For this demo, I have used the CSV format to populate this table. Next, you need to choose the project and the dataset where this table will be created. In the table type option, you need to choose whether you want to create the native table or the external table. Native tables are backed by the native BigQuery storage. In this case, your actual data will be stored in the BigQuery storage. On the other hand, external tables are backed by storage external to BigQuery. In this case, data is not stored in BigQuery storage. In fact, this table just has reference to data that resides in external data source like Bigtable, Cloud Storage Bucket, Google Drive, or Cloud SQL. Currently, this option is disabled for me because I am using the local file system to upload the data into this table. If I use some other option like Cloud Storage Bucket or the Bigtable, then this option will be enabled for me and then I can decide whether I want to create the native table or I want to create the external table. Here you need to give the meaningful name to your table. Next, we need to define the schema for this table. Let me add few columns for this table. This table schema will give you the count of people with the same name and the gender for the given country. Here, you need to choose if you want to create partition for your table or not. A partition table is a special table that is divided into segments called partitions that makes it easier to manage and query your data. By dividing a large table into smaller partitions, you can improve the query performance and you can control the cost by reducing the number of bytes read by the query. You can partition your table either by the ingestion time or some other date or time based column or the integer based column. Like here, you are getting option to create partition based on the count column because it's a integer based column. For this demo, I will not create any partition for this table. In case of CSV import, you can select other settings as well under the advanced option. Like you can choose your field delimiter. Here you can specify the number of header rows that you want to skip. So let me skip my first header row. I will leave remaining settings as default. Now click on create table. So here your test table is created. If you want to preview the data inside this table, then click on the preview button over here. And here you can see the sample data in this table. You can query this data in the same way as you did with the public dataset. Here you just observe the table expiration for this table. If you want to modify this table expiration, then you can do that by clicking on this button. Here you can change the table expiration for this table. If you specify the table expiration at the table level, then this value will override the table expiration that is defined at the dataset level. So this diagram here represents the typical data processing pipeline using BigQuery. Here, first you need to ingest data from various external data sources like cloud storage, cloud SQL or Google Drive, and then create internal tables using the ingested data. Once your data is ingested into BigQuery, then you use BigQuery for data analysis purpose using SQL-like queries and visualize this data using any BI tool like Data Studio. So now we have discussed various data storing services provided by Google Cloud. Now next question is how to decide the right solution for your use case. To decide the right solution for your use case, you can always use this decision tree. This tree can easily guide you in choosing the right solution for your use case. Like for the unstructured data, you prefer to use the cloud storage. And for the RDBMS requirement, you have two choices. Either you can use the Cloud Spanner or you can use the Cloud SQL. If you need horizontal scalability for your RDBMS and your customer base is spread across all the regions, then you prefer to use the Cloud Spanner. Else, Cloud SQL will be the better choice for you. If your data is hierarchical in nature and you need to use the mobile SDK, then you should prefer to use the Firebase DB. Else, you can use the Cloud Datastore. For any kind of analytics workload, if you want to update table frequently or you expect the low latency result, then you should use the Bigtable because Bigtable is a database and it is designed for the large and the scalable application. You should use Bigtable when you are making any kind of app that needs to read and write the data, and scale is the potential issue for such app. Please keep in mind that Bigtable is not a relational database and it does not support the multi-row transaction. Also, it is not good solution for the small amount of data. If your use case is the OLTP transaction, then you might need to look at the Cloud SQL. If you do not expect the low latency in result for your analytics workload, then BigQuery is the better choice for you. BigQuery is a query engine for the dataset that do not change much or change by appending. It is a great choice when your queries require a table scan or need to look across the entire database. You prefer to use BigQuery when you have collected a large amount of data and need to ask question about it. This is all about the data storing offerings in GCP. If you have any queries regarding this, please post your queries. In this section, we will learn about the big data processing options in Google Cloud. Here, we will primarily talk about some important offerings from Google which allows you to perform the big data processing in GCP. These are Dataproc, Dataflow, and Cloud PubSub. Whenever your business expands, it becomes essential for you to do the processing of very large amount of data, do the stream processing, and query the very large amount of data. You also need to do the machine learning for the data analytics part. For all these requirements, you prefer to use cloud-based big data services which can support such use cases because cloud solutions provide almost infinite scalability with very minimum maintenance overhead. Executing such kind of a workload in your on-premise data center is always a pain because of its maintenance overhead. Also, managing the Hadoop cluster in your on-premise data center has the drawback of high fixed cost and low utilization. So let's start our journey to learn about the big data offerings in Google Cloud, starting with the Dataproc. Dataproc is a managed service that allows you to create Spark or I would say Hadoop cluster in Google Cloud. And you can run workloads for the batch processing, querying, streaming, and machine learning using such cluster quite easily. Dataproc runs Apache Hadoop and it allows you to spin off new Hadoop cluster very quickly. And you can easily migrate your existing application based on Hadoop or the Spark technology with very minimal changes. In case of Dataproc, you can use Spark and Hadoop clusters without the assistance of an administrator or any special software. You can easily interact with the cluster and the Spark or the Hadoop jobs through the Google Developer Console or Google Cloud SDK or the Cloud Dataproc REST API. With Cloud Dataproc, you can quickly start, scale, and shut down your cluster, and each of these operations take around 90 seconds or less on an average. This means you can spend less time waiting for the cluster and you get more time to work with your data. In managed Hadoop service in Google Cloud, computation is separated from storage. When you use Dataproc as a managed service to run your MapReduce jobs, then your computation is generally performed by the compute engine VM and data is stored in GCS bucket in place of HDFS. Once you are done with your job, you can shut down this Dataproc cluster to save cost for you. And use of managed deployment, logging and monitoring in Dataproc allows you to focus on your data and not on your cluster. When you run Hadoop or the Spark cluster with hundreds or thousands of nodes in your on-premise environment, then one of the major concerns with such cluster is their high cost and the low utilization of resources because machines are not running all the time. But if you run such cluster in Dataproc, then you can easily manage your Hadoop cluster and save money by shutting down the cluster when you do not need this. Dataproc clusters solve the issue of high fixed cost and the low utilization. And because of these advantages, many organizations are now shifting towards the cloud-based Hadoop cluster. And this has seriously impacted the business of organizations like Cloudera. Just like Hadoop, Dataproc also has master and the worker node configurations, where master node manages your storing of data and running the parallel operations using the MapReduce, while worker node actually stores the data and runs computations for you. When you create Dataproc cluster in cloud, then in addition to the standard Hadoop or the Spark, you can also choose to configure other optional components like Zookeeper, Presto, Zeppelin Notebook, etc. Now let me show you how you can create your first Dataproc cluster in Google Cloud. To create your first Dataproc cluster in Google Cloud, you need to select the Dataproc option under the Big Data. Now click on Create Cluster button. When you create Dataproc cluster in Google Cloud, then you have complete freedom to choose how many master or the worker nodes you want to create and what will be the configurations for these nodes. In addition to this, you can also control the networking and the security aspect for your cluster. So let's begin with our first Dataproc cluster creation. To create your first Dataproc cluster, here you need to provide the cluster name and the location in terms of region and the zones where you want to create the cluster resources. So let me give the names to my cluster. I will keep the location as it is for this demo. Next, you need to choose what kind of cluster you want to create. You can create either standard cluster with one master node and multiple worker node, or you can create the cluster with one node only, which act as both master and the worker. This configuration is generally used for some proof of concept only. If you want to achieve high availability, then you prefer this configuration which run with three master node and the multiple worker nodes. For production use case, this configuration is generally preferred. For this demo, let's go with the standard option only. Here you can select what OS image you want to use for your nodes, and you can change this default image by clicking on the change button. From here, you can choose either any predefined standard image from this list, or you can choose the custom image if you have created any in your project. For this demo, let's go with the default image. If you want to access the web interfaces for the various components of your cluster, like web interface for Yarn or the Spark job, then you can enable this checkbox. I will leave this option as it is for this demo. If you want to configure additional components for your cluster like Jupyter Notebook, Zeppelin Notebook, Presto, Zookeeper, etc., then you can select those components from this list. These components are not installed in your cluster by default. If you want to install any of them, then you need to choose them explicitly from this list. I do not want to select any components from this list for this demo. So let's go ahead. In this section, you can choose the configurations for your master and the worker node. Here, you can configure things like type of machine, number of CPU, and the amount of memory assigned for your node. You can also choose the size of disk and the type of disk as well. So I will change these default configurations for my nodes to reduce the cost. I will use E2 standard machine for both master and the worker nodes for this demo and reduce the size of disk as well. In addition to standard worker nodes, you can also add secondary worker nodes in your cluster, and you can use the preemptible VMs for these secondary nodes to reduce your cost for this cluster. These preemptible instances are those that can be taken by the platform at very short notice. But such preemptible VM can provide you cost benefit of up to 60 to 80%. There are some guidelines to keep in mind when allocating the preemptible VMs to your Dataproc cluster. If your Hadoop job does the map-only operation more and do not rely on the HDFS a lot, then you can probably use the 80 to 90% preemptible VM without seeing the performance degradation. And on the other hand, if your Hadoop job does the lot of data shuffling, then using more than 50% preemptible VM could be a bad idea. In this case, preemption of lot of VM can significantly slow down your job, and additional processing for the fault tolerance might end up even increasing the total cost. For this demo, I will not use any secondary node. In this section, you can configure the networking aspects for your cluster. Like here, you can select the network in which you want to create your master or the worker nodes. Here, you can associate the network tags with your nodes, and you can also attach the labels with your nodes from here. If you do not want to assign public IP to your VM, then you can select this option. Here, you can also define the schedule to delete your cluster to save your cost. And here, you can define the cloud bucket to hold the staging data for your job in the cluster. I will use the default setting for this demo. Here, you can configure the security aspects for your cluster, but I will use the default settings for this demo. Now click on the Create button to create your cluster. It will take some time to create your cluster. I will pause this video till then. So here your data proc cluster is created with two worker nodes. If you want to see the details of your data proc cluster, then click over here. Here you can see the name of your data proc cluster and the status of your data proc cluster. Here you can see the various graphs related to the monitoring of your data proc cluster, like you can observe yarn memory, yarn pending memory, yarn node managers, HDFS capacity, and the CPU utilization over here. If you want to see the VM instances for your data proc cluster, then click here. Here you can see that there is one master node in your data proc cluster and there are two worker nodes in your data proc cluster. If you want to check the other configurations for your data proc cluster, then click on the configuration tab. And here you can see the other details related to your cluster. If you want to make any changes in your data proc cluster, then click on the edit button. So here you can change the number of worker nodes, or you can also change the number of secondary worker nodes for your data proc cluster. You can also attach the labels to your data proc cluster. Here you can see the list of jobs that has been submitted for your data proc cluster. Currently there is no job that is submitted for your data proc cluster, so this list is empty. Now next we will learn how to submit a job for your data proc cluster. In previous demo, we learned how to create a data proc cluster in Google Cloud. Now it is time to run some job in that cluster. To submit the job in the data proc cluster, click over here and then click on the submit job button. Here on this page, first you need to select the region where you have created your cluster and then select the target cluster. After this, you need to select the type of job that you want to run on this cluster. Dataproc cluster supports various kind of job, like it supports Hadoop job, Spark job, Spark R job, PySpark job, Hive, Spark SQL, and Pig job. For this demo, I will use the Spark job. Next, you provide the name of the main class inside your jar. Next, you provide the location of jar that contains your job. Currently, this jar is locally present in your master node, but it can also be present on the cloud storage or the HDFS as well. Here you need to provide the additional argument that you want to pass to your main class. Now to submit the job, click on the submit button. So your job is successfully submitted and now it's doing the calculation related to your job. So this job is completed now and it has successfully calculated the value of pi, which you can see over here. This is how you can submit your job to the Dataproc cluster so easily. So far, we have learned how to run the big data workload in cloud using Dataproc. So after Dataproc, next important big data processing solution in Google Cloud is Cloud Dataflow. So what is Cloud Dataflow? Google Cloud Dataflow is a cloud-based data processing service for both batch and real-time data streaming applications. It is a completely managed service and you do not need to manage the service to process your workload. It enables developers to set up the processing pipeline for integrating, preparing, and analyzing the large datasets such as those found in web analytics or the big data analytics application. It allows you to execute pipeline within the Google Cloud Platform ecosystem. It is a completely serverless approach where users can focus on programming instead of managing the server clusters. And it can be integrated with Stackdriver, which allows you to monitor and troubleshoot the pipeline as they are running. Google Cloud Dataflow was announced in June 2014 and it was released in the beta version to the general public in April 2015. A data flow pipeline is a sequence of steps that reads the data, transforms it in some way, and writes it out. Since data flow is designed to process very large data sets, it distributes these processing tasks to a number of virtual machines in a cluster. So they can process the different chunks of data in parallel. Because it works in cloud, Google Data Flow is a next generation ETL tool that allows business to extract the data from database in their system and transform it into useful data without limitations. You can build a range of important pipeline jobs for the information migration between the Cloud PubSub, Datastore, BigQuery, and Bigtable to build your own information warehouse in the GCP. Some of the important features of Cloud Data Flow are fully managed data processing service, automated provisioning and management of the processing resources, automatic horizontal scaling, work rebalancing, exactly once processing, friendly pricing, and unified programming model. Since it is a serverless offering in Google Cloud, it minimizes the pipeline latency and maximizes the resource utilization, which reduces the processing cost of per data record. Data flow automatically provides the data-aware resource auto-scaling, and it allows companies to horizontally scale their worker resources for the very best performance. In case of cloud data flow, data inputs are partitioned automatically and constantly rebalanced to achieve the faster processing. Data flow jobs are built per second based on the actual use of data flow batch or the streaming workers. Additional resources such as cloud storage or PubSub are built separately as per the pricing of the corresponding service. It means that you do not pay for anything that you are not actively accessing. In a world where accuracy and reliability are key, Dataflow offers the inbuilt support for the execution that is correct and consistent, regardless of the cluster size, and processing pattern for both streaming and the batch data. Google's Cloud Data Flow system uses the Apache Beam SDK for doing the MapReduce operation, data windowing, and accuracy control for both batch and streaming data. One of the primary benefits of using the Apache Beam is that it provides a portable programming layer. It means that it is agnostic to the platform that runs the code. For example, a pipeline can be written once and run using any supported backend. Apache Beam Pipeline Runner translates the data processing pipeline into the API compatible with the backend of the user's choice. And currently it supports all these backends like Apache Apex, Apache Flink, Apache Spark, Google Cloud Dataflow, and Hazelcast Jet. And some of the use cases where data flow is used are point of sale analysis in retail world, fraud detection in financial industry, personalized gaming experience, IoT analytics in healthcare and manufacturing industries. With Apache Beam, we can construct the workflow graph or the pipeline and execute them. Let's try to understand some of the key concepts needed to understand the processing pipeline using Apache Beam. The key concepts include the high-level container that represent your pipeline and the data that flows through the pipeline and how you manipulate the data using the transform. In Apache Beam, a pipeline refers to the high-level container of a bunch of data processing operations. Pipeline encapsulate all of the input and the output data along with the transformation steps that manipulate the data from the input to desired output. A pipeline is made up of multiple steps that take some input, operates on the data, and finally produce the output. Generally, the pipeline is the first thing that you create when you write your code that use the Apache Beam. In more technical terms, a pipeline is a directed acyclic graph and it has nodes and edges that flows in a certain direction and do not provide a way to repeat or get into a loop. P collection are the nodes in your graph and it represents the data in your pipeline. It acts as a way to represent the intermediate chunk or the stream of data as they flow through the pipeline. Because P collection represent the data, you can create them either by reading from some raw data points or applying some transformation to another P collection. Data represented by the P collection could be of any size, ranging from a few rows that you add to your pipeline code to an enormous amount of data that is distributed across lot of machines. In some cases, this data could even be the infinite stream of incoming data that may never end. Transform, as the name suggests, it takes the chunks of input data and converts them into another chunk of output data. In easy way, you can say that it take one P collection as input and turn them into another P collection. By using transform, you can do the various operations on your data like filtering, grouping, joining of the two P collection, data enriching, etc. And Apache Beams comes with various I/O transforms to read and write data to various external storage systems. A pipeline runner runs a given pipeline. Pipeline runner represents where and how the pipeline should execute. And using these three basic concepts of pipeline, peak collection, and transform, you can build some cool things. If you look at this diagram here, it represents the typical Cloudflow stream data processing pipeline. Here, you configure your stream data sources like mobile application or web application to push events to Cloud PubSub topic. And you configure a data processing pipeline in your Apache Beam to subscribe to those events. This Apache Beam processing pipeline does the data transformation and stores the output data either in the Bigtable or BigQuery. And you can run your data analytics query on top of it. After this, you can also visualize this data using the data visualization tool like Data Studio. This way, you can either build the real-time dashboard or call an external API. Now we have seen that we can use both Dataproc and Dataflow to run big data processing workload in GCP. So next big question is how to decide which one we should use. If you have already written some application using the Hadoop or the Spark technology, then you should use the Dataproc in this case, as you can achieve this with very minimal changes in your application. But on the other hand, if you are doing some fresh development, then I would suggest to use the Dataflow because it provides the unified programming model for all kind of workload like batch processing or the stream processing. If you have some specific dependency for running your workload, then you should go with the Dataproc cluster because in case of Dataproc cluster, you have more flexibility in configuring your Dataproc clusters or VM as compared to the Dataflow. Cloud Dataflow is a serverless option, so you do not have much configuration option in this case. Dataflow has less overhead as compared to Dataproc and require less DevOps activity, so it is more preferable for the greenfield project. This table here represents some of the workload type and which solution can be used for the particular workload type. Like for the iterative mode workload or some Spark ML based machine learning models, Cloud Dataproc option is more suitable as compared to Dataflow. Now we have seen that we can use both Dataproc and Dataflow to run big data processing workload in GCP. So next big question is how to decide which one we should use. If you have already written some application using the Hadoop or the Spark technology, then you should use the Dataproc in this case as you can achieve this with very minimal changes in your application. But on the other hand, if you are doing some fresh development, then I would suggest to use the Dataflow because it provides the unified programming model for all kind of workload like batch processing or the stream processing. If you have some specific dependency for running your workload, then you should go with the Dataproc cluster because in case of Dataproc cluster, you have more flexibility in configuring your Dataproc clusters or VM as compared to the Dataflow. Cloud Dataflow is a serverless option, so you do not have much configuration option in this case. Dataflow has less overhead as compared to Dataproc and require less DevOps activity, so it is more preferable for the greenfield project. This table here represents some of the workload type and which solution can be used for the particular workload type. Like for the iterative mode workload or some Spark ML based machine learning models, Cloud Dataproc option is more suitable as compared to Dataflow. If you have used any other messaging system, then you can easily understand the Cloud PubSub very easily. In case of Cloud PubSub, first you need to create a topic and then the publisher publishes the message to that topic. Once this message is received by the Cloud PubSub, then it will assign the message ID to the message that is unique to this topic and will return this message ID to the publisher. Generally, you create separate topic for each message type and it represents the message category. For example, there used to be many departments in a company and when you send message to company, you always call the main number. but your message is targeted for a specific department that depends upon your reason for messaging. Like for any sales related query, you always want to talk to the sales department. Like this. These different departments actually represent the different topics and each of them handles the message targeted for the corresponding department. Now, how Cloud PubSub will determine where to send this message once it reaches to a topic. For this, Cloud PubSub use the concept of subscription. Any consumer or subscriber who is interested in receiving this message creates a subscription with Cloud PubSub to receive this message. And like a work queue, subsequent messages sent to this topic will queue up on each subscription so that consumer can read them later. These subscriptions are similar to queues in other messaging systems, and subscription has three important characteristics. Each subscription receives a distinct copy of each message sent to its topic, and a consumer reading a message from one subscription has no effect at all on the other subscription. Like here, two different copies of the same message are created for the subscription 1 and subscription 2. Each subscription sees all the messages that you send to a topic. This way, you can broadcast the message to different consumers if consumers create different subscription with the topic. Multiple consumers can also consume message from the same subscription. It represents the competing consumer pattern to consume message from the same subscription. This way, you can use subscription to distribute messages from a topic among multiple consumers. But one message can be consumed by one consumer of that subscription. This arrangement ensures that same message is never processed by the two different consumers. It means if multiple subscribers pull messages from the same subscription, only one of them will receive the message. Once a message reaches to the queue of the subscription, it can reach to consumer in two possible ways. Either the subscription can push the message to its interested consumer, or the message can sit around and wait for the consumer to pull it from the subscription. It means Cloud PubSub supports both pull and the push model for the messaging. And once this message is received by consumer needs to acknowledge that it has received the message and process the message, which is called acknowledgement. And for each subscription, you must configure the acknowledgement deadline. If consumer do not acknowledge the message within the configured acknowledgement deadline, then this message will be put back into the subscription queue as if it has never been delivered to any consumer. And this process gives the Cloud PubSub messaging an automatic retry feature. This diagram here represents the supported subscription model for Cloud PubSub. Cloud PubSub supports both point-to-point and publish-subscribe model. In this example, message 2 is only received by subscriber B1, as both subscriber B1 and subscriber B2 compete for the message from the same subscription. On the other hand, both subscriber Y and subscriber Z each receive a separate copy of message 3, as they are subscribing to the same topic C but via separate subscription. This way, separating topics and the subscription is a very nice way to provide both publish subscribe channel and point-to-point channel message consuming patterns through a single API. That is why Google separates the two concepts. Each subscription represents a message queue that receive the message from topic. If multiple subscriptions are attached to one topic, then each of them receive a copy of each message. Some of the common use cases where you can use Cloud PubSub are balancing the workloads in network clusters, implementing asynchronous workflows, distributing event notifications, refreshing the distributed caches, logging to multiple systems, data streaming from various processes or devices, and reliability improvement. I would recommend you to please pause this video and read the examples for each of these use cases. It will help you in understanding how and where to use Cloud PubSub. Now it's time for some practical demo to show you how to create topic in Cloud PubSub and use it to send and receive the message. For this, let's select the Cloud PubSub option under the Big Data. Here you can see the list of topics that you have already created. To create a new topic, click on the Create Topic button. Here you just provide the topic ID for your topic and then click on the Create Topic. Here you can see the details about your topic. Now let's add one subscription for this topic. Before publishing a message to this topic, you need to have at least one subscription created for this topic. So let's create the first subscription. To create subscription, click on the Create Subscription button and then select the Create Subscription option from here. Here you need to provide the subscription ID for this subscription. So let me give the subscription ID for this one. And for this demo, I will use the full delivery type. Here you can modify the other configurations as well for this subscription, like you can change the message retention period over here. It determines how long to retain the unacknowledged messages. Here you can specify the subscription expiry period. This subscription will be deleted after the specified period if there is no activity for this subscription. If you wish, you can also select the never expire option as well. Here you can specify the acknowledgement deadline period. It determines how long PubSub waits for the subscriber to acknowledge the receipt of message before resending the message. For this demo, I will use the default configurations for this subscription. Now click on the Create button to create this subscription. So here your subscription is created and you can see the stats and the configurations for this subscription on this page. In previous demo, we have learned how to create a topic and the subscription in Cloud PubSub. Now let's try to publish the message to this topic. For this, let's select the topic and then click on the Publish Message button from here. Here you can publish either one message or multiple messages at the regular interval. For this demo, let me publish one message. Here you can give the message body. If you want to specify other attributes for this message, then you can add those attributes by clicking on the Add Attribute button. I will leave it as it is and click on the Publish button to publish this message. Now to view this message, click on the View Message button. And here you need to select the subscription that you created in the previous demo. Since we created the pull based subscription in last demo, so we need to click on the pull button to get the message. So here you can see your test message. Since you have not selected this enable acknowledgement option, so you need to acknowledge this message explicitly, else its acknowledgement deadline will exceed after the default period. This is how you can use the Cloud PubSub for sending and receiving the message. In this demo, I have used Cloud Console, but in actual, it will be your application who will publish and subscribe the message to Cloud PubSub. If you look at this diagram here, it represents the typical flow for the stream data processing pipeline. Here, you can configure your stream data sources like mobile application or your web application to push events to Cloud PubSub topic. And you can configure a data processing pipeline in your Apache Beam to subscribe to those events. This Apache Beam processing pipeline does the data transformation and store the output either in Bigtable or in BigQuery. And you can run the data analytics query on top of it. After this, you can also visualize this data using the data visualization tools like Data Studio. This way, you can either build the real-time dashboard or call the external APIs. So this is all about the important tools related to the big data processing in Google Cloud against which you can be tested in your exam. Once you process your data, you can visualize that data using the various tools like Data Lab, Data Studio, Tableau, or Excel sheet. You generally do not need to know in detail about these data visualization tools for this exam. But if you get some question, and you need a detailed video on these data visualization tools, please let me know. If you have any queries related to the big data processing in Google Cloud, please post your queries. So far, you have learned about various services in Google Cloud, ranging from completely customizable compute engine VM instance to completely managed service like BigQuery. When you use so many different type of services in your solution, you definitely need a mechanism to track usage, errors, and activities happening across all such services. This is where cloud logging and monitoring service is used. It is formally known as Stack Driver. Google Cloud monitoring and logging services are part of its operation suite, and it is not only used for Google Cloud, but it is also used for Google's internal infrastructure as well. Earlier, these services are known as Stack Driver. In May 2014, the Stack Driver company was acquired by Google, and in March 2020, Google Cloud Platform announced that it rebranded its Stack Driver monitoring and logging platform to be part of its new Google Operation Platform. Google rebranded the Stack Driver monitoring to Google Cloud Monitoring and Google Stack Driver Log to Google Cloud Logging. Google Cloud allows you to store, search, analyze, monitor, and alert on the logging data and events from Google Cloud and Amazon Web Services. On the other hand, cloud monitoring collects the metrics, events, and metadata from Google Cloud and Amazon Web Services. Google Cloud's Operations Suite ingests the data and generates the insight via dashboard, chart, and alerts. In this section, you will learn about these services and how to capture logs, filter logs, explore logs using the cloud logging, and how to use the cloud monitoring to monitor your applications. So let's start with cloud logging first. Now let me show you how to use cloud logging in Cloud Console. For this, you need to select the logging option under the operations. On this page, you can see all the log entries which are captured by cloud logging, and by default, it shows you the log entries for last 1 hour. Since there is no activity in last 1 hour, so no log entry is appearing for the last 1 hour. Now let me change this time window to 2 months. Now here you can see all the log entries which are captured by cloud logging in last 2 months. And here you can see the list of services to which these log entry belongs to. Now, if you want to filter these log entries and just want to see the log entries that belongs to BigQuery, then select the BigQuery service from here. So now here it will just show you the list of log entries that belongs to BigQuery and are generated in last 2 months. In the same way, you can also do the log filtering based on the log name or project ID or severity as well. Like if you just want to see the error logs, then select the severity as error. And now it will show you the error logs only. So you can see any error log over here. Just observe one thing here is that each log entry belongs to a certain project. And as more and more filter you are applying over here, it is building up a query over here. And you can save this query for the later use as well. Now let's take a look at how a particular log entry look like. Now I will copy this log entry. Here you can see all the fields inside this log entry. Like it contains the name of the log to which this log entry belongs to. It also shows you the severity and the timestamp as well. And if you want to see the payload, then you can check it over here. Now let's go back to Cloud Console. If you want to export these logs to external sync, then you can do that by clicking on the Create Sync button. Here you need to give the name to your sync. Here you can give the description for this sync. Now click on Next button. Here you need to select the type of service that you want to use as a sink. You can use either Cloud Logging Bucket, BigQuery Dataset, Cloud Storage Bucket, Cloud PubSub, Splunk, or the other project as well. So for this demo, let's use the Cloud Storage Bucket. Here you need to select the Cloud Storage Bucket. Either you can select an existing bucket or you can create the new bucket. So let me create a new bucket for this sink. Now click on Next. Here you can see what all logs will be routed to this sink. Now click on Next. Now click on Create Sink. Once this sink is created, then any future log related to the BigQuery will be exported to this sink. Just remember that it will not export any older log entries. Only new log entries will be exported using this sink. So here your sink is created, which will contain any future error log entries that belongs to BigQuery. And these are the default buckets which will contain any other log entries. Now let's understand what is a log-based metrics and how to use them. Log-based metrics allows a logging agent to record certain number of logs for a certain types of messages over a certain period of time. There are system metrics and there can be user-defined metrics as well. System-defined metrics are predefined by cloud logging. These metrics record the number of logging events that occurred within a specified time period. These metrics are free of charge and available to all Google Cloud projects. Here you can see list of all system metrics which are defined by cloud logging. Like this particular metrics count the total number of log entry received, and this log entry counts the total number of log entries that are not exported due to errors. User defined log metrics are created by a user on Google Cloud project. They count the number of log entries that match a given query or keep track of particular values within the match log entries. To create a new user-defined metric, click on the Create Metric button. Here, you need to give a meaningful name and description for your metric. Logging-based metrics can be of two types. It can be either counter-based metrics or it can be distribution-based metrics. All system log-based metrics are the counter type. User-defined metrics can be either counter type metric or it can be distribution type as well. For this demo, I will create the counter-based metrics. Counter-based metrics count the number of log entries matching a log query. For example, this particular log metric will count the number of log entries that belongs to any VM instance. And in the same way, distribution metrics accumulate the numeric data from log entries matching a query. Now let's click on the Create Metric button. So here your user-defined matrix is created. You can edit and delete the user-defined matrix, but you cannot delete the system-defined metric. If you want to see the logs related to this matrix, then click on the View Log for the matrix. So here you can see all the log entries that belong to this particular metric. Let's go back to log-based metrics once again. You can also view this metric in Metrics Explorer, which I will explain later on, or you can also create the alert from this metric. This is all about the logging based metric. Now let's talk about cloud monitoring. What is cloud monitoring? Google Cloud Monitoring is a part of its operation suite that collect metrics from multi-cloud and hybrid infrastructure in real time, which enables you to answer some really critical question in cloud, like, is my service healthy? What is the load on my service? Is my website up and responding correctly? Is my service performing well? You can create custom metrics using cloud monitoring or set up an alerts to notify you of certain events in which you are interested. Or notifies you when the measurement do not have an acceptable values. To explore the cloud monitoring on Cloud Console, click on the monitoring option under the operation. Here you can see various dashboards that will monitor your resources continuously, and you can display data in those dashboards using various graphs. You can also see the uptime checks that you have configured in cloud monitoring. These uptime checks will help you in verifying if your instance or service is up and running or not. You can also see the reported incidents over here. And in cloud monitoring, you can also organize and monitor resources into groups that make sense for your application. You have already seen how to create log-based metrics. In the similar way, you can also create other metrics as well using the Metrics Explorer. Now, before we learn about how to use this Metrics Explorer, let's try to understand what is a metrics. A metric is basically a collection of certain measurement that helps you to understand how your application or the system services are performing. And the application and the system services being monitored are called as monitored resources. Currently, there are 1500 types of metrics available in cloud monitoring to monitor the Google Cloud, AWS, or the variety of third-party softwares. In case of cloud monitoring, model for the monitoring data consists of three primary concepts. These are monitored resource types, metric types, and the time series data. Here, monitored resource represent the resource about which you want to capture the metric. It could be like a VM or cloud storage bucket. And metric type is the measurement that you want to collect about those monitored resources, like disk data use, amount of memory consumed by cloud storage bucket, and so on. And time series represent actual data point values collected about the metric over the period of time. Now let's see how to use this metrics explorer. So now if you want to measure the amount of disk data read by your VM, then you can do that by choosing the resource type as VM instance, and you should choose the metric type as disk read bytes. Now it will monitor the amount of disk byte read for all the VM instances, and you can see this data in terms of chart over here. By default, it will display the data for the last 1 hour. And since there is no activity in last 1 hour, so currently there is no chart appearing over here. So let me change this time frame window to 6 weeks. Now you can observe some data points collected over last 6 weeks over here. You can also change the type of chart that you want to display. Like you can change it to the stack bar chart, stacked area chart, or heat map chart. Let me try the stack bar chart. So this is how your data will look like if you convert this chart into stack bar chart. Here it is showing the disk read byte for each VM, and each VM is represented by the different color. Here you can do various other operations for the data that is collected for this metric. Like you can apply filtering, you can do the group by, or you can do the aggregation as well. Like if you want to filter the data for a particular instance only, then you can apply the instance ID based filter. So if I choose this particular instance over here and click on apply, now it will display the data for this particular instance only. Let me remove this filter. Now it will display the amount of disk data read for individual VM once again. But what if you want to see the total data read each day for all the VM rather than seeing the data individually for each VM? You can do that by applying the aggregator function. Like if you apply the some aggregator function over here, then it will display the total data read each day for all the VM. Now if you want to see this data based on the storage type, then you can do that by applying a group by function. Here you can do the group by based on the storage type. Once you are done with your metric and the chart, then you can save this chart and display it on a dashboard. Here you can save this chart either on the existing dashboard or you can create the new dashboard. So let me try with new dashboard. Now click on save. Now to see this chart in the newly created dashboard, click on the dashboard. From this list, select your dashboard. So here you can monitor your metrics in the form of chart in your dashboard. In addition to cloud logging and cloud monitoring, there are some more GCP services under Cloud Operations Suite, about which you should be familiar with for this exam. These services are Cloud Debugger, Error Reporting, and Trace. You do not need to know in more detail about these services from exam perspective, but at least you must know the purpose of these services for this exam. Cloud Debugger is a feature of Google Cloud that allows you to inspect the state of running application in real time without stopping or slowing it down. Your users are not impacted while you capture the call stack and variables at any location in your source code. You can use it to understand the behavior of your code in production as well as analyze its state to find difficult bugs in your application. Cloud Debugger can be used with production applications, and you can easily collaborate with other team members by sharing your debug session. Error reporting aggregates and display error produced in your running cloud services. It provides the centralized error management interface, which enables you to find your application's top or new errors so that you can fix the root cause faster. You can report errors from your application either by sending them directly to cloud logging with proper formatting or by calling an error reporting API endpoints. Cloud Trace is a distributed tracing system that collects latency data from your applications and display it in Google Cloud Console. You can track how requests propagate through your application and receive the detailed near real-time performance information from this. CloudTrace automatically analyzes all of your application's traces to generate in-depth latency report to find the reason for the performance degradation. CloudTrace can capture traces from all of your VMs, containers, or App Engine projects. This is all about Cloud Operations Suite. If you have any query regarding this, please let me know. So friends, so far you have learned about various services in GCP like Compute Engine VM instance, Cloud Storage, App Engine, Cloud Function, etc. And you created all these resources either using Cloud Console or command line utilities like gcloud or gsutil. This approach of creating resources in GCP is fine as long as you need to create few resources and that too once a while only. But what will you do if you have to create thousands of resources or few resources repeatedly? Definitely, you cannot create so many resources manually via Cloud Console or command line utility. To solve this concern, you definitely prefer to write some kind of a code or a script that can do this job for you and create resources repeatedly for you with just few clicks. And we call this approach of creating resources in cloud as IAC, or you can say infrastructure as a code. When we talk about IAC, then we consider the infrastructure like a software which can be version controlled, tested, and reviewed. You can also put description of the required infrastructure together with your IAC code and can have a complete definition of all that is required in one place. You can start testing and deploying everything together. In case of Google Cloud, Deployment Manager is one such offering which enables you to define your infrastructure using IAC approach. This is very much similar to other tools like CloudFormation in AWS or Terraform for multi-cloud infrastructure support. Google Cloud Deployment Manager allows you to specify all the resources needed for your application in a declarative format using YAML, and you can deploy many resources in parallel at one time. This IAC approach has many advantages like reuse, composability, source control, and testable code. With this IAC approach, you can create reusable templates that can be used again and again without any additional effort. You can use these templates to create different environments like dev, QA, UAT, or production. You just need to create some configurations as per the environment, but the same template can be used to create resources using the corresponding configuration. These templates allow the use of building blocks to create set of resources that are typically deployed together, like an instance template, an instance group, and autoscaler. These templates can be parameterized to allow them to be used over and over by changing the input values. to define things like what image to deploy, the zone in which to deploy, and how many virtual machines to deploy. One template can include or refer another template as well. And this way you can compose a complex architecture. The templates can be placed in a source repository such as Git and subject to all of the associated checks and balances. You can review those templates before rolling it out to create the infrastructure. Deployment Manager allows user to focus on set of resources which comprise the application or service instead of deploying each resource separately. Now, before I show you how to use Deployment Manager to automate resource creation in Google Cloud, first let me explain some of the main terms related to this. And these terms are resource, deployment, and template. Resource is something that you want to create, like VM instance or cloud storage bucket or cloud function. Deployment Manager has concept of a deployment, which is a collection of GCP resources that form a logical unit and that are deployed together. The resources of a deployment can be anything available on GCP, like VM instances, IP addresses, database servers, Kubernetes clusters, etc. You can use Google Cloud Deployment Manager to create such set of resources and manage them as a unit called a deployment. For example, if your team's development environment need two virtual machines and a BigQuery database, you can define these resources in a configuration file and use Deployment Manager to create, change, or delete these resources. This configuration file is in YAML format that lists each of the resource which you want to create and its respective resource properties. And you can make the configuration file part of your team's source code repository so that anyone can create the same environment with consistent result. Each resource that you define in this configuration file must contain three components, and these three components are name, type, and properties of the resource that you want to manage. Name is a user-defined string to identify the resource, like VM instance name or your cloud storage bucket name. Type is the kind of resource that you want to deploy, like VM instance or cloud storage bucket. You cannot give any arbitrary type over here. You can just provide one of the resource type among all the supported resource types. To check the complete list of supported resource type, please refer to Google Cloud documentation. Properties are the parameter for the defined resource type. Generally, for each resource type, there are fixed set of possible properties and its associated value. Like here, in this example, we created a deployment configuration YAML file which creates a VM instance with this name. Here, type is compute.v1.instance, and these are the various properties defined for this VM instance, like zone, machine type, and so on. Template is a reusable file that can be used across multiple configurations. Templates are much more flexible than individual configuration file and intended to support easy portability across deployments. By using these templates, you can build really a complex structure. And template file is written in either Python or Jinja 2. Like in this example, this template file is imported in this deployment configuration file. Now, let me show you how to use Deployment Manager and how to create a deployment in Google Cloud. To access Deployment Manager, click on the Deployment Manager tab under Tools. Here, you can see all your deployment that you have created so far. In this demo, I will use one deployment configuration file, which will be used to create a VM instance. To create a deployment from this configuration file, I will use Cloud Shell, and here I have already uploaded the required configuration file to VM running this Cloud Shell instance. Here you can see that this will be the name of the instance that we will create, and type of resource in this case is compute.v1.instance. And these are some of the properties of the compute VM instance that we will create. Now let's execute the command to create the deployment. So this is the command to create your first deployment. So here you can see that deployment manager is creating a deployment. It can take some time to create an entire deployment. That depends upon the number of resources that needs to be created by this deployment. So here your first deployment is created and you can see the layout or full configuration of this deployment by clicking over here. Here, if you want to see the layout of this deployment, then click over here. And similarly, if you want to see the configuration of this deployment, then click here. Here, you can see the full configuration of this deployment. So let me also show you the VM which is created by this deployment. And here is your VM which is created by this deployment. Now let's go back to deployment manager. Now, if you want to delete this deployment, then select the deployment that you want to delete and click on the delete button. Here, it will ask you if you want to delete just the deployment or you want to delete both deployment and the resources created by this deployment. Here, I will delete both deployment and the resources created by this deployment. Now, let's click on the delete all button to delete both deployment and the resources by this deployment. So your deployment is deleted now. So let's also check the VM. So here your VM is also deleted. This is how you can create resources in Google Cloud using reusable deployment configuration. But before using deployment manager, just remember one thing, that all the cloud services are not supported by deployment manager. Also, in addition to using such custom deployment configuration, you can also use predefined templates which are provided by GCP via its marketplace. This marketplace was earlier known as Cloud Launcher. Here, you can easily find predefined templates for the commonly used solutions. But keep in mind that you have to pay for most of these ready-made configurations. Like if I search for the Redis configuration here I will have to buy this configuration first before launching it via deployment manager. And here I can see the pricing for this deployment configuration. This is all about deployment manager and cloud launcher for this exam. If you have any queries related to this, please post your queries. Now let's try to understand how CI/CD pipeline can be built in Google Cloud. You do not need to know much in detail on the individual service in implementing CI/CD pipeline for this exam, but it is still important to know what are the services involved in implementing CI/CD pipeline in Google Cloud. So basically, there are three services which you can use to build your CI/CD pipeline in GCP. And these services are Cloud Source Repository, Cloud Build, and Spinnaker. You can use these services to build, test, and deploy your code in GCP in a seamless manner. To continuously deliver app updates to your user, you need an automated process that reliably build, test, and update your software. Your code changes should automatically flow through a pipeline that includes artifact creation, unit testing, functional testing, and production rollout. This CI/CD pipeline should allow you to apply code update to only a subset of your users so that it is well tested before you push it to your entire user base. And you call such release as canary release. If your canary release proves unsatisfactory, your automated procedure must be able to quickly roll back the software changes. In Google Cloud with GKE and Spinnaker, you can create a robust continuous delivery flow. Although rapid iteration is your end goal, you must first ensure that each app revision passes through a series of automated validations before becoming a candidate for production rollout. And once your team decide that app is ready for the production, one of your team member can approve it for the production deployment. Now let's try to understand this CI/CD pipeline with a typical development workflow. So this is how a typical development workflow look like for any application. In any development workflow, first developer make the code changes and push it to Git repository. And you can use cloud source repository to host your Git repository. You can also achieve the same result with other third-party products such as GitHub, Bitbucket, or GitLab. Once developer's code is committed in Git, you need to build the Docker image of this code and then validate this Docker image by running all your unit tests. And this whole activity is done by Cloud Build. By using Cloud Build, you can build software quickly across all programming languages, including Java, Go, Node.js, etc. across multiple environments like VM Engine, Serverless App Engine, Kubernetes, or Firebase. Once your Docker image is validated, Spinnaker detects the image and do the canary deployment of this image, and then it performs the functional testing of this canary deployment. Once this canary deployment is approved, Spinnaker deploys the image to production. And this is how a typical development workflow look like for any application. From this exam perspective, you do not need to know how to configure individual service in this CI/CD pipeline, but you must understand at least the purpose of these services.